Okay, good morning. I'm Dr. Eric Rehm. I'm Senior Oceanographer with Seabird Scientific. Welcome to the webinar on BGC data processing, the why and how of converting raw sensor data to meaningful estimates of biogeochemical phenomena. And we're going to focus on two sensors. I wanted to do more, but this totals 4 measurands: the eco sensor, chlorophyll fluorescence, backscattering, and CDOM fluorescence, as well as our Seabird 63 oxygen optode, which has another version called the 83, which is soon to come out. So the principles of converting data from the raw data to the instrument require some sort of or it helps to have an understanding of the instrument, of the metrology, meaning how the conversions are, what they're based in, and their traceability to real standards. So we're going to go over all of that today. Again, we're going to focus on 4 measurands. I think in a future BGC data processing, I would focus on a couple other instruments. So if you see this seminar again, make sure you check it out because we'll probably cover different instruments that time. So you won't be seeing a repeat. And as always, look forward to your feedback. My email is there. Feel free. If there are any questions that don't get answered during the time that we have, feel free to email me or contact me about any of the aspects of this presentation. We're here to help you with using our sensors to get real data. Okay. So we're going to do a little bit on sensor basics, take a look at some calibration sheets, take a look at the sort of the theory of operation of the instruments around fluorometry and backscattering, take a look at how those scale factors, which essentially turn our counts into engineering units, and that's what we call them, engineering units. That just seems to be the vernacular, but the actual scientific numbers that we use, how their traceability. Again, look at calibration sheets again, and take a look at example data. And we'll be seeing some MATLAB and some Python. And then we'll take a look at the Seabird oxygen optode. So again, here are the sensors we're going to take a look at today. We're going to focus on the fluorescence, chlorophyll fluorescence, backscattering, and fluorescent dissolved organic material fluorescence. It's also called CDOM. The FDOM is actually supposedly the correct word, but I'll probably be using those words interchangeably. And we have 2 sets of sensors that right now that provide essentially those 3 measurands, the eco line and then the CL. Some people know this as the MCOMs when it appears on a Nabis float. And then our oxygen optode, the 63. The 83 has a flow-through plenum. I won't be showing that instrument today, but all the processing that applies to the 63 applies to the 83 because it has the same, essentially the same optode underneath. So the basics of a sensor, of the optical sensors that we're talking about today, and actually most of our optical sensors, are that there's some sort of light source, typically an LED, and it shines a light either directly or at some angle into the environment, and or through an optical window. And then there's a photodiode, which is sensing that volume and is getting scattered light. Now, in the case of fluorescence, when fluorescence is excited, it turns out the photons basically go everywhere, which is kind of a nice thing. So you're kind of guaranteeing fluorescence that the sensing volume is going to have fluorescent photons coming back to the photodiode. In the case of the oxygen optode, there's actually a sensing element, which is where the fluorescence interaction happens. In that case, the sensing element itself is what is observed by the photodiode. And the arrangement's a little different, but the principle is the same. From an electrical point of view, this is an oversimplification, but you can imagine that there is a battery or some kind of power source that's turning on the LED. You have your sensing volume or sensing element. You have a photodiode that outputs probably a very small signal, some sort of amplifier, and usually there's some other signal processing here, especially in the optode, because that uses essentially a it looks at the phase of a signal relative to its emitted signal. So there's some other signal processing, but an amplifier and other signal processing to make this signal bigger. And then we goes through what's called an ADC, an analog to digital converter, where it's converted into digital numbers. And that's what you see on the output ultimately. And it's usually some ASCII and some instruments binary format. Optionally, our sensors may have a clock and some memory. The ones we're looking at today, I won't focus on that part. We'll assume that the platform itself provides, time and other aspects of it. So we'll just be looking at the most simple sensor configuration. And just as a note in the lower left, you see that in general, we actually don't just power on the LED during while the instrument's on. It actually flashes, not just at the rate that you see, because that's when it's going, essentially turning on different LEDs in the eco, but it's actually modulated. It's turned on and off at about 1,000 times a second. And as you noticed in these pictures, we have the sun in here, and the sun could be interfering with that measurement. So what we do is we take a measurement with the LED on, and then we take a measurement with the LED off and essentially subtract that, because that'll get rid of the ambient light. So that's the basics, really, of how all of these sensors work. Let's take a look at fluorometry here. And for those of you who attended the session last week, there's a few slides that are repeat, mostly just because they're good at explaining the phenomena. But chlorophyll fluorescence is a phenomenon of the chlorophyll molecule itself. And chlorophyll is important in that it accepts light and is the beginning of photosynthesis, which the ocean gives you every 1 of 2 breaths of oxygen that you breathe. So oxygenic photosynthesis is absolutely imperative for the survival of the planet. So if you take spinach or any green plant, chop it up, extract the chlorophyll, turn out the lights and shine an ultraviolet or even just blue light on it, it will fluoresce in the red. It's the liquid is the same in the 2 pictures. So it's not the color of the liquid. We're seeing that red fluorescence because those red photons are actually being emitted. This is not an absorption phenomenon in this case. So what is fluorescence? A photon enters the environment, and as for those of you who saw the presentation last week, a photon only has several fates. It can either live or die. Live meaning it's scattered. A photon dying means energy has been absorbed, and once it's absorbed, it essentially then has 2 further fates. It could be, or 3 further fates in the case of photosynthesis. It can be transferred into the photosynthetic chain, essentially being the battery for photosynthesis. If there's too much light, some of those photons are just converted to heat, just as waste heat, but some of those photons are converted into fluorescence. And in the bottom right of the picture is showing essentially as light is absorbed into the various energy states of the atom, it can be 1 or more of them. There can be some internal interconversions between those spaces, but in the case of heat or fluorescence, it drops down. And notice that the gray and red hours are shorter than the blue. And if we think of those as the amount of energy the photon has, a fluoresced photon has always a little bit less energy than the absorbed photon, and that results in essentially a shift. So a photon, if you remember the spectrum from violet out to red, as you move to longer wavelengths, you are in essentially slightly less and less energetic photons. So we have what's called the Stokes shift. So a blue photon, for example, in this case is absorbed. Some of those interconversions take place. The fluorescent photon is always a longer wavelength. And so this is the basic principle of fluorescence. So in the case of chlorophyll fluorometry, the absorption spectrum on the top. So what we're seeing is a graph of the absorption of photons or the ability of the pigments in phytoplankton to absorb light. On the horizontal axis is wavelength, on the vertical axis is the absorption coefficient. So you can see at 430 nanometers, which is essentially about a violet color, there's an absorption peak. There's another absorption peak at around the red at 662 nanometers. But the fluorescence emission spectrum, again, is always to the right of any of the absorption peaks for the material. So it's certainly to the right of 430 and is certainly to the right of 662. So we see that same Stokes shift. And here is the fluorescence equation. Again, I went over this last week, but I'll go over it very quickly again. The fluorescence is essentially a product of several phenomena. The light source, which we control, so that essentially is a constant that we know or can calibrate. The absorption of phytoplankton that's normalized by chlorophyll. And the intuition here is that if I have twice as much chlorophyll, I have twice as much pigment, and then I have twice as much absorption. So you could think of that as just with paint. If I have a pigment in paint at the paint store, if I add twice as much of that pigment, the paint would be that much darker in whatever that color is. And so essentially the chlorophyll is just a scaling constant for the absorption. That light is absorbed, and then the last factor is a physiological factor. But again, we assume it's a constant for the purposes of measurement. And this is the how much of those absorbed photons are turned into fluorescent photons. That's called quantum efficiency or quantum yield. So if we essentially bind up those physiological factors along with the light, essentially we come out to an equation like this, where the fluorescent photons is just some factor times chlorophyll. So this is an important concept right here, that we have both the ability to calibrate or understand the relationship of a, we can use this relationship to calibrate an instrument from first principles. We have some known amount of chlorophyll. We measure F, the photon, the fluorescent counts, and we come up with K, or 1 over K, which is our scale factor. But when we have, we'll go over how that works in metrology later, so I don't want to get ahead of myself. So I wanted just to show you here the calibration equations. So we have something that looks very much like that in the first line. Chlorophyll A is a scale factor times fluorescence counts. Let's just briefly take a look at fluorescent dissolved organic material fluorescence. A lot of the carbon that's in the ocean, in fact, a majority of it is actually dissolved, much like why your tea or coffee is brown. It's because there is a dissolved substance in there. In this case, it's hard to see in most cases, but we have sensors that can sense it through fluorescence. And out of that total pool of organic matter, there is, which includes particulate matter, there's some of it that's dissolved organic matter, DOM or DOM. And then a subset of that is the amount of dissolved organic carbon, DOC. A subset of that actually has chromophores, or is colored, again, that we can sense that color, and we can use a variety of instruments to do that. But even a smaller subset of that is the stuff that's fluorescence. Now, it's not generally true that you can develop a direct relationship globally between fluorescent dissolved organic material and dissolved organic material, certainly, or total organic material, but there are regional relationships, and it is interesting to look at these dynamics of that portion of the carbon pool in any case. So that's why we have those sensors. And again, if we look at this, we're looking at what's called an excitation emission matrix. Along the bottom is the excitation wavelength. Along the vertical axis is emission wavelength. And one can imagine scanning an LED. Let's say we had a LED that we could vary the color of very easily and scanning it along. And again, notice that diagonal line means that the emission wavelength is always greater than or equal to the excitation wavelength. And those colors are just showing the intensity of the fluorescence. The little boxes are showing essentially what portion of that excitation emission relationship, somewhere around 360 excitation and 460 emission, that various vendors' fluorometers, including our own under our former name Wet Labs for the optical instruments. So the width of those two light blue areas have to do with the essentially bandwidth of the excitation LED, and the horizontal bar, its height corresponds to the width of the emission filter, which you can see is a lot wider. Where those intersect red box that I just drew is essentially the fluorescence that we are sensing. Notice that we're not using a very, very short excitation wavelength. First of all, such short wavelengths are a little dangerous and they're difficult to power. But secondly, you can see that we're getting maybe in the first quarter, first third of fluorescence response. This particular excitation emission matrix is not, or the excitation emission matrix is not universal. This particular one is looking at river water. There are different constituents in the ocean that are slightly different. In any case, to convert from the actual instrument counts to the actual measurement, in both cases of fluorescence, we take our digital counts, remove what's called the dark counts, and this is just the background, essentially the noise that's in the sensor, which is constant. Remove that, multiply it by a scale factor, and that's how we're going to get the engineering measurement. Let's take a look at the third measurand that's in an eco-sensor backscattering. And I'm not going to go into all of the theory of operation, but the basic idea is that when light interacts with a particle, you can see that it can scatter light in all sorts of different directions. You can, in this case, it assumes a photon coming, directly down from the sun into the ocean. But you can imagine if it's an LED, this kind of diagram could be in any direction. The important thing is that the way the shape of how much light is scattered in what direction has nothing to do with the amount of illumination. It's called an inherent optical property. It has to do with the size of the particle and its relative size and shape, its structure. For example, the structure of a phytoplankton with respect to its internal shell or test, or its a physical structure. Its length, its aspect ratio, these all go into it. So it's a property of the particle itself as to how those little arrows are arranged in what direction. And backscattering is interesting because when we do look at ocean color satellites, we want to look at the light that is essentially goes into the ocean and turns around and comes back up and can be sensed by a satellite. And this is the one piece of calculus in the whole thing, but I'll explain it. What it's saying is the backscattering is essentially just the sum of all of those arrows in one hemisphere. And that's what that hemisphere looks like in the blue. Now you say, well, how do we really know what backscattering is? Well, we've had some people who've worked for the company that have developed some innovative instruments. Here's an instrument that essentially, you can see that ring. That's a ring of optical detectors at all sorts of different angles. All those angles that you can see between the two red arrows up there with the symbol theta. And we've actually measured that integral, and we know what backscattering is. And surprisingly, if we measure at one angle, and again, on the left, we see a sensing volume, just like we saw in the early sensor basics picture, where we have a detector coming out at an angle and a source illuminating at one angle, a detector measuring that sensing volume, and you can see that sort of trapezoidal volume. The blocks here are just one slice through that whole volume, but the whole volume, that trapezoidal volume, is what's contributing to the backscattering signal. We're only measuring it at one angle, and you say, hey, don't we need to measure it at this? Doesn't everybody need to use one of these? And the answer is no. We took that instrument and did millions of measurements and found that if we just measured at one angle, let's say 124 degrees on the bottom right, we can come up with a factor, a constant factor that we can multiply that measurement at one angle by and get the total backscattering value. And that's like, wow, that's great. So let's take a look at the bottom at this equation here. So what we're measuring with the instrument is a measurement called beta, which is essentially how much light is scattered at in the case of an eco, 124 degrees at 700 nanometers. That's the red LED that we use. And we get to that number the same way we got to CDOM and chlorophyll fluorescence. We take the digital counts, subtract off just the baseline of the noise in the sensor itself, inherent just through semiconductor physics, and multiply that by a scale factor. Then to get the total backscattering signal, it's really just a bunch of constants after that, one of which is a little funny. We want to get the backscattering due to particles alone, so we need to subtract off the scattering at that one angle, and that should be 124, not 123. take the scattering of the water molecule itself. And it turns out we know that. We can do some math and we have a number for that. So it's not a constant. It's dependent on the angle, on the wavelength, on temperature and salinity. But as long as we have those four numbers, we can subtract it. And then we multiply it by that chi factor, which was from here. So for 124, it's about 1.01. And then 2 pi has to do with the spherical geometry that's involved. So it's not a big leap to go from measuring at one angle to measuring, essentially getting a hemispherical value. Let's take a look at how those scale factors are determined. I'm not going to cover all the instruments. I'm going to cover mostly just fluorescence, but the same applies more or less to the same principles apply. So it's important to know that when you go to the store and you buy a ruler, how do you know it's 1 meter or 1 foot? And that's because you say, well, how could they possibly sell a ruler that didn't match that? It sounds like a Monty Python skit. People would be measuring, doing this. The word foot probably came from the king's foot, which varied from king to king. Not a good traceability tool if you wanted to, base taxes, perhaps based on the king's foot. But the important thing here is that there's a traceability from the industrial measurements, which in case are your measurements, to a secondary laboratory, which is us, to a primary laboratory, which might be the instrument supplier that we get our laboratory reference instruments from, and they will tie their instruments to a national metrology institute like the National Institute of Standards and Technology, and ultimately into what we call SI units, which is meters, kilograms, seconds, and so on. And there are international and national institutes that keep track of those things. So here's the main picture here with respect to chlorophyll metrology. Chlorophyll metrology means essentially how do we trace when you take that scale factor and multiply it by some counts and you get some a chlorophyll concentration, just like the ruler, how do you know you're getting a number that is the right number, that we haven't just started some really sort of bizarre Monty Python skit here with respect to chlorophyll? Well, what happened was a long time ago when the eco was first designed and first being vetted, we grew a culture of a single species of phytoplankton. This is a lab rat of phytoplankton. It's a diatom, which is one of the most ubiquitous genuses of phytoplankton, especially during the spring bloom and fall bloom period. They're not tiny, but they're not too large on individual. They can form chains. And this one happens to be called Thalassia westphalogii. And we didn't actually keep any records of how the light conditions, the nutrient conditions that was grown under, because those can affect the chlorophyll concentration. But what we do know is that this experiment was carried out and the chlorophyll content of those things were assessed using a standardized method, a method that has been it was written in protocols, for example, by EPA. It's called EPA method 445, but essentially it involves filtering water, and you can see that apparatus in the upper right here, filtering water under filter pads that put into a test tube with acetone. That acetone essentially leaches the pigment out overnight. They're sonicated, centrifuged, and then we take a look at that, essentially just like that green fluid you saw in the cup in the early part, but we use a standardized fluorometer, laboratory fluorometer, and independently assess that. And so we know essentially what the chlorophyll concentration is of various dilutions of this culture. And then we take our primary, the first ever eco that we ever built. It actually wasn't that, but just imagine that just for the moment. And we say we know a certain amount of chlorophyll. We have a certain number of counts. We divide the two and we get a scale factor. And then we say we've got this golden instrument and it's tied to this. It's traced to an actual experiment with real phytoplankton culture. So there's the tie. So this is a little bit like the king's foot, because what if we picked a different culture? But that's a real problem in ocean biology, because we know that the phytoplankton community varies all over the ocean. And this is actually a pretty good starting point. In the resources at the end of this thing are some good, there's at least one paper that talks about this choice of species of phytoplankton, how representative is. If you're more concerned about that, consult that paper. But the important thing is that we came up with a laboratory determination of chlorophyll. We essentially calculated a scale factor for this primary reference fluorometer. We then transfer that by doing a similar experiment, but now we don't need to use a phytoplankton culture anymore. We can use any fluid that fluoresces in the range. And because phytoplankton cultures are expensive and hard to maintain, in this case, we use a uranine dye, which is just essentially a common food dye, food. And I think, I'm not sure if it's used in printing, but it's a yellow dye. And it fluoresces very much like chlorophyll. But at that point, it doesn't matter whether it's chlorophyll or not. What we want to do is just make sure we can replicate the instrument response. So we have a certain amount of fluorescent dye. It doesn't have to be exact. We take our primary reference fluorometer, use its scale factor, and compute essentially an equivalent amount of chlorophyll. We have our secondary reference or production fluorometer. It reads a number of counts, and we go through that same exercise again. We have a known amount of chlorophyll, divide by the counts, and we have a scale factor for the new instrument. The whole point here is we can trace essentially your production scale factor back to a secondary reference fluorometer, which is tied to the primary reference fluorometer, which was tied to the laboratory determination of chlorophyll, which was tied to this original culture experiment. Now, you'd say, well, golly, you did that once. You sure it works? Well, we did it again this summer, and it does work. We took probably a decade-old primary reference fluorometer, went through these first two steps again, and voila, we got exactly the same chlorophyll measurements that we got 10 years ago on that particular instrument. We don't use it a lot. We just use it to calibrate our secondary reference fluorometers. And when these show any signs of aging, we replace them. When we use this one rarely. This was just a little bit about the species of diatom that we used. And just to let you know, how do we know that that laboratory fluorometer is right? Well, we calibrated that laboratory fluorometer using, again, a traceable standard that we paid a lot of money for. And so we are relying on the laboratories that make those chlorophyll standards, where they extract the chlorophyll, again in acetone, and do a very careful measurement. So here's just an example of that first step, where we have the laboratory concentration from the calibrated laboratory fluorometer on the horizontal axis, the eco counts of our primary reference fluorometer on the vertical axis. It's that slope, that's the scale factor, that relationship between a chlorophyll measurement and the counts that gives us the primary scale factor. And again, this is the experiment that we did this summer, which looks at the chlorophyll that are eco read from the historical, and then the laboratory fluorometers measurement. And you can see it does very well, except down at the very, 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 very low concentrations where there's more uncertainty. When we get into the other end, when we do a production fluorometer, again, the process is the same. In the production fluorometer, we have a horizontal axis of essentially our I'm sorry, I have these axes mislabeled. I apologize. They should be switched. No, that's right. The secondary reference is on the vertical axis in chlorophyll units. On the horizontal axis are the counts of the production sensor. And again, it's the slope that gives us now the production scale factor, the one that you get on a calibration sheet. With fluorescent dissolved organic material, the thing is the same, except our primary reference now, instead of being a phytoplankton culture, is a chemical mixture, which is essentially is a de facto standard for all fluorescent dissolved organic material fluorometers across the industry, regardless of the manufacturer. We make a preparation of that and make it at different concentrations. And again, relate the actual preparation, laboratory preparation concentration, in this case, zero, which is ultra pure water. And in this case, just 2 concentrations, and relate that to the instrument counts, and we get a slope. So let's take a look at some calibration sheets. The calibration sheets essentially tell us what that scale factor is. And again, that scale factor can be traced back to a primary reference, but that's the slope of that line that we were just talking about. That's the number you use in this equation. The other one that you need is the dark counts. That's one that you can update yourself just by taping off the sensor with black light, preferably then immersing it in water just so that you give it a constant temperature, hopefully matching our calibration temperature, and you can always update this amount, but this is what we did. Let it run for about 5 minutes at least to get going, and there's your 48 counts. So we take the instrument output, subtract off the 48, and multiply by 0.0073, and voila, we have chlorophyll concentration. Backscattering, if you remember, this is scattering at one angle. We have that second equation, which gives us total backscattering, but we take the scale factor and multiply it again by the output minus the dark counts. Same principle, even though it's a very different measurement, right? It's not fluorescence, we're talking about scattering. And notice this linear relationship. It's true in chlorophyll, it's true in backscattering, and it's true in CDOM. And that just, we're lucky. That's just the nature of these physical measurements, that essentially we can detect this scattering, and it is that the amount of light that we measure in that scattering volume, that trapezoidal scattering volume, is linearly related. Essentially, we are truly sampling this. And yes. And then we have CDOM, the same thing. So in all these cases, the information that you need are the first 2 lines, the dark counts and the scale factor. So let's take a look at some example data. What we're going to be taking a look at is another vendor's float, NKE. It's a French float company that has all of our various sensors on it, including an eco sensor. And this particular one was deployed and lived for about 1, 2, 3, 4 years, 2013 to 2017, which is the average lifetime of a float. This is a biogeochemical float, which means it has all sorts of biogeochemical sensors, again, including the eco. And we're going to be taking a look at the 12th profile that it ever did. It was deployed not far from Iceland in the space between the east side of Greenland and Iceland. There's still a little bit of influence from the coast here and this long ridge, and you'll see that in the data. So it's profile number 12 of this Argo float. All the floats, just like all the ships in the world, have a unique number. This one was 690-1486. And if we just plot all of the counts together, and so let's take a look at the data here. On the leftmost panel, we have just output from the CTD, temperature and salinity. And as an oceanographer, I'm obligated to always show you that, because physics rule, and physics are really important even in biological measurements. But it also lets you know if your code is working right, because temperature and salinity, even though salinity is computed from conductivity, these are measurements that you know that come essentially right out of the CTD, and you can plot them very easily. You don't have to typically go through a calibration equation to use them. Now in chlorophyll A, we're just looking at the counts. So we have, in this case, 0 to about 600 counts. In the case of backscattering, we have somewhere between 0 and 250 for the main part, but you can see these little spikes, some of which are many times the baseline over here. And we'll talk about why that is in a moment. And then for fluorescent dissolved organic material, we don't see a lot of variation, but there are some. And that can be explained from, there are several biogeochemical explanations for that. Going back to backscattering, what are these little dots that are way out here? Are these sensor noise? No, they're probably really true phenomena There was phytoplankton up here, so we can see that there's what's called a subsurface chlorophyll maximum at about 100 meters. So there's a lot of chlorophyll there. There are a lot of phytoplankton. Some of them are dying. They've been eaten or dying. They're sinking, and those particles enter occasionally into the sensing volume, and you get a little spike. So just like the pops that you used to hear on vinyl, when you hit a pit or a piece of dust in the vinyl and you hear a pop, this is the pop of the ocean with respect to particles. Fluorescent dissolved organic material, one can think of as you go deeper in the ocean, it's sort of older, especially with respect to ocean circulation. And as material ages, it removes itself from the light of the ocean, and it isn't degraded anymore, and you get kind of a constant background of fluorescent dissolved organic material. Now, all I've done between these two slides, I've gone from counts and look in the upper left, engineering units. I've subtracted a number and multiplied by another number. That's a linear relationship. They don't look any different, but the horizontal scale has changed, of course. Now we can see that we have somewhere between 0 and 2 milligrams per meter cubed of chlorophyll. We have somewhere between 0 and 0.006 inverse units of meters of backscattering. And we can see that based on quinine sulfate dihydrite equivalent units, that chemical that we use as our primary reference, as our standard, we have about somewhere between 1.9 and 2.5 of those units. And here we are. So what does the output of an eco look like? It looks something like this. I picked an eco that does not have a real-time clock or memory, so the date and time is no longer there. Why would you sell such an instrument? Well, if the platform itself, the mooring, the glider, the float, the buoy has its own data logger that has the ability to timestamp each one of these records, well, there's no reason to add that additional cost into the instrument. In this case, we're just looking at the raw output of the instrument from left to right. We have date and time, which are constant, no clock. We have a constant column, which has to do with the emission wavelength of chlorophyll. It's just a marker. It's telling you that, in fact, this is a chlorophyll column in the next column. There's the actual digital measurement. Next column is the same thing for backscattering. It's at 700 nanometers. Again, constant all the way. And then 310 counts. Likewise with fluorescent dissolved organic material, we're measuring it at roughly 460 nanometers. And we have, it shouldn't be 63.5. I don't know how it got there because the digital counts are our digital numbers should be 63, 64, 65. You can see that that number isn't that high above dark counts. It's only about somewhere between 10 and 15 counts above. And that's because there just isn't that much CDOM in the ocean, open ocean. In a coastal environment, those numbers would be much higher. So let's take a look at some MATLAB code. And I am going to temporarily switch screens here. So I am going to stop sharing, do a new share. And we're going to go here. And can you, Nicole, can you confirm you're seeing the full screen MATLAB?
Yes.
Okay, so we're looking at a very simple program. The program is called eco counts to ENG. And what I've got from that float is that data that you just saw, and even though it says comma separated value, those values are separated by tabs. So it's a tab delimited file. I've used the MATLAB read table function just to read that data in, and I've overridden the column names since they're not in the file with date time, that excitation wavelength, the counts, again, the excitation wavelength, and again, the counts of backscattering, again, excitation wavelengths of CDOM, and again, counts for CDOM. And so it's really these counts, that's the data that we're interested in converting into engineering units. This is really just algebra at the end of the day, but we do need that calibration data. So what I've done is hard coded just from the sheets that we saw before, that scale factor and those dark counts, and some other information that we need. We know that the backscattering due to seawater, we have to know what the wavelength is, and we need to know what that angle is, 124 degrees. And we need to know what that chi factor is. And you can get that from either from this paper, which is in our resources, or you can get it from the Argo documentation, which is also listed in the resources. And here's that same equation that we saw before, right? So we take our counts, subtract off the dark counts, multiply by the scale factor, and we've got beta. Remember, in the case of backscattering, we're not done. So the second step is to compute backscattering due to seawater at 124 degrees and 700 nanometers. Well, I have a function provided by the guy who wrote the paper that does that. So all I have to give it is this calibration wavelength, temperature, the scattering angle, and salinity. In this case, I'm just going to fix those. And you probably don't remember, but that's about the value at about 200 meters. 6 degrees centigrade was the temperature, and the salinity was 35 units at about 200 meters. And there we are. There's our 2 times pi times the chi factor times the total scattering minus the saltwater scattering, which gives us, just leaves us with a backscattering. And so if I run this file, I get a graph. Notice that I haven't plotted it terms versus depth. I've just plotted versus sample number. So if we, rotate our head to the right, we'll see again above on the top graph, we see counts, and at the bottom we see the sample number, and they look exactly the same because all those transformations are linear. It's just the vertical scale that's changed, but this is the one you can publish. If we had 2 different eco units with backscattering, these number of counts might be slightly different due to differences in a resistor or an LED. It's the process of our calibration and that calibration coefficients that guarantees whether there's some changes in this from instrument to instrument, that you would always get the same number. So our goal is that if we had 1, 2, or 20 eco fluorometers that had backscattering meters at 700 nanometers, they would all line up on the same axis. So let's just take that one more step. I do have, since this is a float with a CTD, I do have access to the CTD data, which I've conveniently put into a CSV file. And I also have access to the actual pressure coordinates of those eco. If they weren't available, let's say like on a glider, typically use the time axis, and you can interpolate the glider's pressure, onto the time of the values for backscattering and temperature and salinity and so on. So the only difference in this particular case is we're going to read those CTD values and the eco pressure values. I'm going to add that pressure to the table. I'm going to read the CTD data. I'm going to throw away any data where there is essentially a missing value. And then I'm going to interpolate the CTD data onto the eco pressure coordinates. That's an important step so that you have the temperature and salinity exactly where the eco was measured. In the case of a glider, this might be using time instead of pressure, as I mentioned before. Again, I've sort of essentially created a little calibration sheet, but in MATLAB code here, everything is the same from down here, from now on in the code, except that now instead of T, well, let's say first I run it with the constant T and S, but then in this particular case, this routine needs to be run for each value. It doesn't, unfortunately, take vectors because of the way the person wrote this routine. So I just write a little loop where I feed in the temperature and salinity at every one of the values. And if remember, N is the number of eco values that we have. And so let's take a look at what that looks like. And what we're going to do here is just run it and make this bigger. And so we see on the left, again, temperature and salinity. For some reason, temperature has gone a little wonky on me this morning, but we can see the backscattering. And in the case of the red, this is the backscattering using the constant temperature and salinity, and the green is the backscattering value, particulate backscattering value when we used a depth dependent. And then I just took the difference. And that really is telling us essentially what the effect of using what the error was in assuming a constant temperature and salinity. And that worked pretty good, actually, up to about 200 meters where it crosses 0, which is the point at which I chose that 6 degrees and 35 salinity units. Down deep, the signal gets a little bit noisier. And as we know, we're getting much, much colder, and the scattering properties of water being either temperature or salinity dependent are more evident. So those are that. We can also take a look at this in Python, essentially the same thing. And what I've done, and this is something to look forward to, we're developing a set of tools in Python that will be available to the general public that you can download and use. And so for backscattering, here's the API that we would give you. And again, it takes in everything that you need. Counts from the output of the instrument, the dark counts, the scale factor, the scattering angle, the wavelength, that chi factor, and then the temperature and salinity to get the backscattering or backscattering due to seawater. And the code is remarkably the same. We're going to compute the counts minus the dark times the scale factor. That looks a little funny. It's in quotes. It doesn't look like a math expression. This particular Python package called numerical expressions is really wicked fast and highly parallelized. So this is essentially an optimization for speed to use this particular package, but it makes it very clear what the equation is. Then, just like in the MATLAB code, we've gotten the scattering at 124 degrees, 700 nanometers at a vector of temperature and salinities. And this is nice. This particular implementation is nice. Doesn't matter whether it's a scalar or a vector. I didn't have to write that loop. We subtract off the scattering at 124 degrees from the total scattering to get the particulate. And then we multiply by 2 times pi, the chi factor, and that value, and that gives us our scattering. So let's take a look at the main routine. I basically created a little function, which is essentially a database for the calibration coefficients using a dictionary. At some point in the future, we're looking at a web-based service where you could just send in the serial number and the model number, and you would get this back, and you could dynamically query for that data with perhaps the option for you to locally cache the results for your own instruments. And most likely the server would return information in a format that looks a little bit like this using the JavaScript serial object notation or JSON. And we're working on metadata standards that all vendors will hopefully adhere to, that make it so that no matter what vendor's equipment you're using, you'll get a similar structure. So here's our main program, which is a lot like the MATLAB version. We read in the eco data, give it some column names, get that calibration data from the data above. I'll make this a little bit bigger, and essentially call our API again with the counts, all the calibration information, temperature and salinity, and do the same thing for chlorophyll and FDOM since we're here, and create a figure. So let's run this program. And we have to find where it turns up, and unfortunately ends up on another screen, which I'll bring over. And you can see, again, I just have, in this case, three, if you want to call them time series graphs of the backscattering with those spikes, the chlorophyll with that subsurface chlorophyll maximum, and the CDOM, which varies. And it's kind of a noisy signal because it's very close to detector counts. So voila, there we are. So I am now going to switch back for the moment to the presentation. And desktop. Oops, 3, I think it was. Is that right?
Yes, you were using 3 before.
And let's see. So you seeing the full screen?
We have the presenter view. So if you can swap the displays.
Okay. Oh, there we are. So do you have that
Perfect.
now?
Yeah, looks great.
Okay. Ended up slightly different arrangement. I'm looking to the right of the camera. It doesn't mean I'm not paying attention. So we went through and we saw the code, the MATLAB code here. I seem to have lost control. Oh, there we go. Okay, good. I'm back. Okay. So there was our MATLAB code. Here is the MATLAB output of the table, which we saw. Here was the graphical output that we looked at. Here was the Python API, just to remind you, since you won't have access to the full code yet. And here's the Python API being called. Here's the pandas data frame, that's output. And again, those time series graphs. So that's how we got for 3 measurands on an eco, got from counts or essentially instrument units into engineering units. Let's take a look at the Seabird optode. I'll go through this quickly since I know we don't have a lot of time left, but the optode has an optical window. It uses a principle of fluorescence. So if you take a look in the upper right and focus on that, we have a blue LED that essentially illuminates a film, a foil through which oxygen diffuses. And the oxygen that diffuses through that changes not only the intensity of the fluorescent photons shown there as the red squiggles, it also changes the lifetime of that. And I'll show that in the next slide. You see on the left, if there is no oxygen in the environment and we give it a pulse, the blue pulse on the left, and then we see the time decay of fluorescence detected by the photodiode. We see this exponentially decaying thing. If we essentially increase the partial pressure or the concentration of oxygen in the water, not only does the height of that change, but the lifetime of that emission changes from 65 microseconds to 25. Now, it turns out it's pretty easy to screw up the amplitude measurement, but it's not. It's very difficult to, if you can measure that lifetime. And so we do that. Just take a look at the bottom by essentially the blue pulses are modulated according to a wavelength, according to a sine wave. And we can see on the bottom left in number C, we get 65 microseconds. That long lifetime corresponds to a phase shift between the peak of the blue and the peak of the red of 63 degrees. If we go to the bottom right, D, and we increase the pressure of oxygen in the water, the phase shift is now less, it's 38 degrees and corresponding to a lifetime of 25 microseconds. And that lifetime is essentially directly proportional to that phase shift. So if we can measure the phase shift, we can measure the lifetime. Notice again, a very nice linear relationship. I've included a little slide here as to why the red sensor is there, but basically it's a reference sensor. It's not involved with stimulating fluorescence, but you'll have that explanation. Again, it's the blue LED that's doing all the work with respect to fluorescence lifetime, and the red helps normalize those things. So what does the code do? The code essentially takes CTD data, temperature, salinity, and pressure, and it can compute density from that. Takes the O2 sensor, that phase information, which again is essentially directly proportional to the fluorescence lifetime and the temperature. And the code then produces oxygen in a number of different ways, in milliliters per liter, micromolar, micromoles per kilogram, or the partial pressure of oxygen. Further, we can take the same CTD data and come up with an oxygen solubility, which is independent of the measurement, but that's how we get oxygen saturation. We take the oxygen value and divide by its solubility, of course, using the same units. So in processing this data, we have a little toolkit that takes the actual voltages that are output by the optode for temperature and turns that into temperature. That's the first line. The second line takes that phase and the temperature and the calibration constants, and then temperature and salinity as promised, and turns that into an oxygen concentration. And that's a series of about a half a dozen, 6 to 8 equations that have all sorts of empirical constants in it, as well as the calibration coefficients. Oxygen solubility, you can see, is a function of temperature and salinity, and a flag that just has to do with some processing options that we use versus those used by Argo. Again, this is a property of the water, not an oxygen property, but then we calculate the oxygen saturation by taking the oxygen value in milliliters per liter and dividing it by the solubility computed in the same units and multiplying by 100. And when we do that, to the left, we see essentially the density of the water. That's important in computing the oxygen in micromoles per kilogram, since that relates a volume of water to a mass of water. But more importantly, we've computed oxygen concentration and oxygen saturation for that profile. Again, this is the same. This is actually for a float that is currently off Hawaii, and this data is fairly recent, from September 18th. Just to note that this is just some late-breaking work, that we have some ability to undo some of the pressure effects, and look forward to seeing more of that in the code for the SPE 63. So in summary, Seabird makes tools that help oceanographers understand light in water, or anything in water, any biogeochemical quantity. Our relationships take into account the linear relationships between the optical response of the environment to controlled sensing and the biological phenomena of interest. And we measure some of the most important proxies for biogeochemical processes, including phytoplankton biomass through chlorophyll fluorescence or particulate scattering, ocean carbon, and ocean oxygen. Okay, I know I haven't left a lot of time for questions. You'll find in this slide deck some resources.
Oh, all right. If anyone has any questions, please go ahead and type them in the Q&A, and we will see how many we can answer in the few minutes we have left.
Yes, the first question by Julia with respect to the reference the paper that I just mentioned regarding different cultures used to calibrate. Take a look at this last paper by Colin Ressler in 2017. And again, the PDF version of these slides will be available. Is that true?
Yes, we will upload the recording of this session onto our YouTube channel, I would say within a week. And we will make the PDF of the slides available on our website.
We've got just a moment if there are any other questions out there. I hope you found this useful. Clearly, we have other instruments from which we have essentially counts or some sort of sensor measurement, which isn't in physical units, and those get converted to physical units. Please let us know if there are particular instruments that I didn't cover today that you would like to see covered, because I started out with essentially the simplest ones, but and I had planned to cover more, but as I got into developing the slide set, I wanted to make sure, like, the issues of traceability back to standards was well covered, so that you essentially know where that scale factor that we're using and that you end up with comes from, so that that, as I said, when you go to the store and buy a ruler, you're confident that it measures a meter or a foot. And we're in that same business and want you to know that we have a reliable basis for those measurements. Could you suggest any resources in learning about lighting and metrology? Metrology is I would look for anything from the National Institute for Standards and Technology. if you want to jump in feet first with all the math around uncertainty, there's a thing called GUM, literally GUM, Guide to Uncertainty and Measurements. But you'll find a lot of online resources that help with that. Secondly, lighting, I would take a look. There's an Ocean Optics web book. I did not include it in the useful papers. It is a URL, but just Google Ocean Optics web book. Or there is a book called Light and Water, which is available as a free PDF, which is the sort of Bible of optical oceanographers. But start out with the Ocean Optics web book. I think you'll find it useful, and it kind of takes things at different levels, meaning there's an introductory, medium, and expert level to go through the web book with. Well, thank you for attending. Again, I appreciate you taking time out of your day to come to this seminar, and don't hesitate to send any other questions you might have to Seabird, including me personally at erehm@seabird.com.
Thank you, Eric. Thank you, everyone. If you have a minute, please fill out our survey and give us some feedback on these sessions afterwards. Right, take care.